Well, I'm back with an update on the IC tester. I've been doing quite a lot since the last update. As you can see, we've now got 12 volt and minus 5 volts, and we've got a memory button on the screen. Everything else looks just about the same. If we go into the memory option, we get the chance to test SRAMs, DRAMs and EPROMs. I've got SRAMs working, I've got EPROMs working. DRAMs, well, that's another story which we'll come to slightly later. If we look at the SRAMs, at the moment I've only got a couple of chips in there, but it's easy enough to add new ones. If we go in and look at EPROMs, we've got 2708, 508, 532, 716, 732, and again it's quite easy to add new ones. Right, something else I've added is the capability for testing high impedance states when doing chip tests, which makes them more thorough and it gives much better confidence in the state of a chip. Now, something you might be wondering about are these white dots on the front panel of the IC tester. Unfortunately, being a skinflint, when I was putting together the board, I decided I would pinch these switches off the previous version, and it wasn't until I'd got all of the SMD components mounted, all the through-hole components mounted, and I did my first tests, I found out that in my desoldering I'd managed to damage this switch, this one, and these four over here. So the next version I will be putting new switches in, but for the moment, unfortunately, it needs to look like this to work properly. So these jumper wires are just taking the place of the switches which have been damaged. It's a pain, but as I say, I'll fix it on the next go around. Just to demonstrate how the high impedance testing works, this is just a little array of resistors which plug into the chip tester. Like that, and then into there like that. And then if we were to do a test on this chip, which is a 40107, let's do a test. 40107 gives that the thumbs up. If we go into the exercise mode, now this chip has got open collector outputs. So it's a NAND buffer or driver, so because both inputs are low, the output is open collector, so that just is in high impedance state. So if we go into immediate mode, as soon as we turn both inputs on, the output goes off and is pulled low. So if we put any of the inputs high, the output goes into high impedance state again. Now this is obviously fairly clunky, and the next version of the circuit board for the IC tester will have these pull-up, pull-down resistors built in, and you won't have to plug them in or anything. So that's looking at the high impedance on a 40107. So I've put a 4094 in the socket, so I'll give that a test. So serial in, parallel out with output latches, and it's tri-state. And if we go and look at the exercises for this one, so what it does is it just clocks in an alternating pattern and checks that all the outputs are as they should be. Okay, and the last test, it actually raises the lowers the output enable pin, and that puts all the outputs into high impedance state. So if we just flip into immediate mode, we can then flip that pin up and down. You can see the output pins going into and out of high impedance state. So that's the high impedance testing. So let's now have a look at memory testing. So memory memory testing. As I say, we've got SRAM working and EPROM working. I'm going to stick this in, which is 2112. So I'm going to SRAM testing to 2112. Okay, it now knows that this particular chip has exacting power requirements, and it's going to want to talk us through those. I won't go through how it does that at the moment, so we'll just skip that, and I'll tell you what we'll do. We'll hook up 5 volts on there. We'll take that jumper out, see what a pain that is. So we'll put 5 volts on pin 16, and we'll put ground on pin 8. Okay, so we'll skip the power up. So here it's telling us it's a 256 word, each word being 4 bits, which gives us a total of 1024 bits. We've got various tests that we can implement, so we can turn these on or off as we want, or we can just let them run. We'll do all of them to start with. And we've got a random test here as well, and we can do that 10, 100, 1000 or 1 time. So I'll just leave it at the default of 10, turn all the tests on, go. So the purple is as it writes data, and the green is as it successfully reads it back. So that one's passed with flying colours. And again, just to show you, we'll go back into the 2112, switch off some of the other tests. Now when it does the walking ones and walking zeros tests, which are where it puts a 1 into the first bit with zeros and all the other bits, writes all of those, checks that they're all okay, then it writes just a 1 into the second bit and does the same again. And with the walking zeros, it's the opposite, where it sets 1s in all the bits and then walks zeros across them. So we'll do 100 tests in the walking ones and walking zeros, and you'll see that when it does the walking tests, it does them 4 times each before it moves on. There we go. And up here we've got the overall progress of the test. So this is a really thorough test. It's randomly writing words into the memory and verifying that the data is being read back correctly. Nearly there. There you go. That's a good one. Okay, just to show you it with a 6116 chip in. Hang back in a second, I just need to do a bit more rewiring. Okay, so I popped 6116 into the socket, do a memory test, SRAM, 6116. Again, we've got the power pin set up, but I've already done it. Okay, and just to talk you through the tests, we write all 1s into every memory location, all 0s, alternating pattern of 1010, alternating pattern of 0101, alternating patterns of 1100, alternating patterns of 0011, write 0 to 15. That's just a bit of a test. We've got the walking 1s and walking zeros I've talked about, and the random test. Now what I'll do is I'll change the random to 1 for this test, and there we go. So the progress bar at the top, it shows in light green for the standard tests and then dark green for the random tests. So because this is an 8-bit chip, we do walking 1s 8 times, we do walking zeros 8 times. Just to show you what happens if there is a fault on the chip, what we'll do is we'll use the dip switches here to break one of the data lines mid-test. So we'll go back in and test the 6116, and we'll set the random count to just 1, start, okay, and then we'll flip a data bit and go get some test fails. So they show in the individual test whereabouts in the memory the failure has occurred, and they also occur in the overall progress bar. Nearly done. There you go, failed. Okay, so I've popped the 2708 UV EPROM into the socket. I've hooked it up to the -5 and 12 volt supplies, which are generated from the incoming 9 volts on a little circuit board underneath, which I'll show you shortly. So we're going to do a test on a 2708. Because it's an EPROM, there's not a lot you can do to test it, but again, we've got the power pin set up, which will talk you through connecting which pins to which power supplies. Skip that. So what we can do is we can take a binary dump of the contents of the PROM. We can take an ASCII dump. We can so both of those go into a file on the SD card. We can take a serial dump, which will show the contents on the serial monitor of the Arduino. We can view the dump on here, and we can do a multi-read. And what that does is it reads the EPROM, generates a checksum, and then just keeps reading the EPROM and validating that the checksum on each pass is consistent. So if we're going to do a view dump, okay, so we've got the address in hex, we've got the hex content of each of the bytes, and we've got the ASCII version of those. We can page through this if we want. Right, and if this was a bigger EPROM, more buttons would appear here to go backwards by 1 page, 10 pages and 100 pages, and forwards by the same amounts. So this is a 2708, so it's 1024 words of 8 bits, which is why we get 2 digits in the hex. If this was a 4-bit memory chip, we'd only get 1 digit in the hex for each column, and we'd be able to see 16 rather than 8 per row. So there you go. That's the serial dump, sorry, the view dump option. Go back in again. Right, if we do a binary dump, that reads the contents and it's written it to 2708 and it gives it a random number. Right, and if we do an ASCII dump, it will do the same as if it was doing the view dump that we looked at, but it'll be 16 columns wide, and I'll show you that shortly. If we do, by you looking at the serial dump, if we do a multi-read, there you go, it's calculated the checksum is 90 and it's now reading through it, and if it detects any inconsistencies it'll show you those, and all you've got to do to stop it, touch the screen, and away we go. Okay, so what I'm going to do now is I'm going to go and do a memory test on that EPROM 2708, and I'm just showing you the output of the serial port on the Arduino. So 2708, right? You can see there that it's this is as it's reading the configuration file for the memory tests. So it shows us the name of the chip, what type of chip it is, number of pins, data bits, address bits, how many words, how many bits. How many address bits, shows you the address pins and the data pins, how the power pins are configured, which is a bit of a kludge at the moment, which is the CE pin and which is the OE pin. So now that it's got those, I can then skip the power setup, and if I do a serial dump, that's what we get. So there you go, there's the address. From 0 to F. Here's the ASCII. Request to set pin state when the pin is not an output. Pin 256. That's a bug, right? We'll have to fix that. Okay, so there's the actual dump of the memory contents. And if you were to do an ASCII dump, then it does just the same as this, but writes it to the file on the SD card. So here is the Excel spreadsheet which I use to generate chip specifications for the tester as a whole, and in this case for the memory tests. So it's a simple Excel table. It's got the chip ID, the type of chip, number of pins, the number of data bits, number of address bits, number of words, number of row address select bits, number of column address select bits. Those are generally used for DRAM, obviously, rather than the SRAM or the EPROM. We've then got the pins that are used for address, the pins that are used for data. I'm just in the process of implementing for those odd old chips that have got separate data input and data output pins, but generally those would be the data pins that are required, and in here, as in the case of the 2115, data comes in on pin 15 and goes out on pin 7, so I'm just implementing that at the moment. which pins the power is on. So that's 5 on pin P, ground on pin H. In this one, this is the 2708, so that's ground on pin L, 5 volts on pin X, minus 5 volts on pin U, and 12 volts on pin S. As I said, that's a bit of a kludge at the moment. We've then got various pin definitions, so row address select, column address select, CE pin, WE pin, OE pin, CS pin, and the pin numbers are negative if the pin is active low. We've then got the pin directions, which are how they are set up initially, and the initial pin state. Now there's going to be some extra bits in here for things like timing, but this is how you can easily specify a new chip if you want to in terms of memory. So all you need to do is update this from the datasheet for a particular chip that you want to add, then poke the export memory button with the SD card in a reader on the PC, and Bob's your uncle. The next time you install the card in the IC tester, you've got new memory testing capability. Okay, right, let's have a look inside. Okay, so here's the tester with its top off, and if we just pop the board out, the main board. Okay, so here's a little power supply board in the bottom. It's hooked up to the main incoming power on the Arduino. It's got a 7660 voltage converter in there, the appropriate capacitors and things to make it generate the -5 and the 12 volts. We've also got a couple of relays up here, and the output, the power outputs from this power supply can be switched on or off by the Arduino such that you can validate that the connections of power to the chip are correct before the -5 volts and 12 volts are actually applied to the chip under test. That's just to protect things. However, that's not implemented yet because these connectors here and here are required to drive those relays, and this board doesn't yet have the capability to do that. But it's all tested and it all works, and the next version of the board would do that. Up here, where there used to be a header that you could use to drive the real-time clock module, because I had to put the power supply in here and the relays got in the way of that connector, or vice versa, I've had to add these two bodge wires to continue to allow me to make connections to I2C devices, just in case you're wondering what that's all about. There's a connector there, so if you need to take the power supply out, you can do without having to disturb the Arduino. Right, now it's time to talk about the elephant in the room. I've renamed this from the Mega IC tester to the Magic tester, with the oddball font, because it's IC tester obviously. But I've been becoming more and more dissatisfied with the capabilities of the Arduino Mega. I am currently using every single one of its outputs, and I want to be able to support chips with more pins than 24. The only EPROM I can really test is a 2708 or a 2508, because the other ones are, there are other chips I could test, but generally the limitation of 24 pins is not good enough, I'm afraid. So therefore I did consider using 23017 IO expanders or 23S17 IO expanders, which are driven by I2C or SPI, but it all became a bit of a pain in the chunks, so I've decided to go a completely different route. I have got another version of this board designed which supports RGB LEDs down the side to show you the status of pins and guide you in connecting up power supplies and things, but the other problem that I've ran across is that if I want to do DRAM tests, DRAMs require refresh cycles to ensure that the contents of the memory don't disappear, and the Arduino Mega just isn't up to it. It only runs at 16 megahertz, and even using the most tuned I/O that I could only really get to refresh once every 7 or 8 milliseconds, and that's without doing any real processing, and that's just too much of a limitation. So I've decided to that the Magic IC tester is dead, and I'll have to do something else. So at the moment I've stopped development of the hardware on this, and I'm going to do something else which I'll show you shortly.